All right, how's it going, everybody? We are here on Friday, February 19th, and today we're going to talk about section 7.5, our strategy for integration. Um, and the sentence at the top of the screen right now, I think, says it all right here. You guys should recognize that there are only two summary sections in this entire textbook that covers three semesters of calculus and then some. Like, we don't even cover all these chapters in 3 semesters of calculus. And that's because integration's hard, and it's worth our time to kind of stop and recollect ourselves after these last sections 1 through 4 here in chapter 7, all the stuff we saw in chapter 5, all the uses of integration that we're going to see coming up in chapter 8 for our next application chapter here. So it's good to kind of like stop and kind of like I feel like it's in these times where everybody's kind of got their integration horse blinders on, and it's good to kind of like stop and like look left and look right and kind of like see the landscape a little bit better here. So that's kind of what we're going to talk about today. We'll do some more integration today, but we're also going to kind of talk a little bit of big picture stuff here. So with all the integration we've been doing, one thing that we might wonder to ourselves is like, how much integration is there that we could technically do? Can we integrate all continuous functions? And the answer is not even close. And when I say not even close, I mean that there are ways that we can measure the fact that out of all continuous functions, now when all of you go to grad school and you take measure theory after you take real analysis, you will define some things like measure density of a set, and it can in fact be proven that the of the set of all continuous functions, the set of functions within that set that are integrable has measure density of 0, meaning that there are infinitely more non-integrable functions than there are integrable functions. Okay, that last sentence right there was a bit bad non-technical phrasing right there. But anyway, the point is, most stuff isn't integrable, right? So while it's really important for you to conceptually think of integration and differentiation as inverses, and remember, almost inverses, that plus c kind of screws some things up. Remember that we lose information when we ask for an antiderivative because we're saying what function has these particular slopes, and there's always going to be a vertical shift associated with that. Our location does not matter for slope measurement, right? So that's what my asterisk is indicating right there. So it is equally important to acknowledge that they are not on equal footing with our ability to perform those actions right there. Differentiation is something that a mathematician would refer to as a one-directional operation. One-directional operations are things that are easy to do in one direction and are difficult to impossible to do in the other direction. Our examples of one-directional operations are differentiation, right? We can take the derivative of pretty much any continuous function. It doesn't matter how nasty it gets. You multiply 16 of them together, you make all these compositions happen, whatever. I can chain rule and product rule myself to success in every case. It might take me some work, but I'm just following like a very few number of formulas and known differentiations. Integration, we've learned that that's not true. You multiply two weird functions together and you're screwed, right? Another example of a one-directional operation is multiplication of prime numbers, right? When I say one-directional, I mean it is easy for you to multiply any two numbers together. If I asked you to compute 13 times 17, any of us could either do that on paper, or you could go to a calculator and do that. I'd consider that to be an acceptable a thing to do there as well. And the reason I would consider it fine, and I don't consider it cheating at all to go to a calculator to do this operation right here, is because the inverse operation of performing multiplication is factoring, undoing the multiplication. If I were to say to you, hey, go ahead and factor this number right here. Tell me what its prime factors are. The reason why I don't consider it cheating for you to have a calculator for the forwards direction is because even if you had a calculator for this backwards direction, trying to determine the factors of 612,701, you still couldn't do it. And when I say you couldn't do it, I mean you would probably have to sit there for over an hour just trying stuff in your calculator. The going backwards version, way, 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 way harder than the going forwards direction there, right? And by the way, this number right here, just so that you don't spend all day doing this, because I know you guys are just gonna sit there and try and find your primes right there. This is 631 times 971. Being able to figure out a factorization for some number that's not prime, really, really, really difficult to do. A third thing here that's a one-directional operation is a computation of an MD5 hash. These are things that you have indirectly interacted with hundreds of times in your life, but you probably don't know it if you don't know what an MD5 hash is. What an MD5 hash is, and I'm going to try to explain this as simply as possible, is when you, for example, download a program from the internet, how does your computer know that you actually downloaded all the stuff, right? How does it know that it didn't miss like one single tiny packet of information and the whole thing's not going to work when you open it? Well, what it's going to do is it's going to take all of the data within the program, or for very large programs, a subset of the data, and it's going to build a polynomial using some of the data, and it's going to plug in as an x value into the polynomial a bunch of the rest of the data. It's going to produce an output value that is going to be some like 32 integer, so 32 place number, um, perhaps applying a modulus, where perhaps the modulus is actually also determined from some of the data that you've downloaded right there. And the point is, for any program that's written where some company is putting their program out onto the internet, they are going to, in their own corporate headquarters, they are going to determine what the MD5 hash output should be from that operation, so that on your computer, when it downloads it, will also compute the MD5 hash of all of that data. And again, just get a number out of it, just like a 32-bit number. And then it will compare the MD5 hash on your computer to the one that that corporate headquarters is saying that you should have got. And if your two numbers match, then we are incredibly, incredibly confident that you got the full download successfully. So when we know that your computer successfully downloaded something, how do we know it didn't just miss something? It's because it's computing an MD5 hash of all of the data and comparing it against the known correct MD5 hash from what should happen if there's a known guaranteed perfect file right there. So MD5 hash comparisons are kind of how we validate data when we transfer data, which is an interesting thing. And it ultimately just ends up being a bunch of really fancy polynomial math. The math behind it is not too terribly complicated. I've written my own MD5 hasher as part of like a little brief internet course that I did. It wasn't really too hard. It's a kind of complicated idea, but not like, I don't know. It's within your grasp, like certainly. The point, though, is if you were to tell me what the MD5 hash was of some data, there is absolutely no way for me to determine what data you took the hash of. There's absolutely no way to do it. And it's not hard, like factoring numbers is hard. This is like straight up impossible. For one, it's not a one-to-one function, so when we do the inverse, there technically would be multiple possible answers, but it's not even possible to come up with what your possible answers would be. Undoing that operation is proven not possible because of the degree of the polynomial that are involved right there. So all of these are one directional operations. It's really easy to do their forward direction. It's either very difficult or impossible to do the backward direction. And I think it's really interesting to think about like what things in life are one directional operations. What are things that you straight up can't undo? And I mean, integration falls into this with differentiation, right? Differentiation we can pretty much always do. Integration, we rarely get so lucky as to find a special case that we can actually handle by doing a ton of work, right? It's a one-directional operation, differentiation. So let's define something else here. An elementary function is a function that's made up of, these are the operations, and these are the functions you're allowed to use, right? You're allowed to perform the operations of addition, subtraction, multiplication, division, and composition between our standard families of functions. You should read this list and recognize that this is basically what you learn in college algebra and trigonometry, aside from the fact that nobody talks about inverse hyperbolic functions, and that's okay. So any combination of polynomials, rationals, powers, exponentials, logarithms, trig, inverse trig, hyperbolic, inverse hyperbolic, using any of the operations, addition, subtraction, multiplication, division, composition, all of those functions are what we refer to as the elementary functions. They are composed using elementary operations between elementary functions, our simple functions, and we collectively call those elementary functions. So the thing is that given this definition of elementary functions, we can prove that we can take the derivative of any elementary function, and very importantly, it is guaranteed that we are always going to get back another elementary function anytime we take a derivative. So this is the idea of closure in mathematics. We would say that the set of elementary functions is closed under the operation of the derivative. Performing that operation on one member of the set is guaranteed to return to you another member of that same set. As a counterexample, think about things like division and the integers. The integers are not closed under division because it is possible for me to do a division between two integers and to get back a number that is not an integer. 2 divided by 3 just popped us out of the set of integers, right? So this idea of closure says closure is associated to both a set and an operation. And it says, are you able to perform this operation on an element or elements of the set? Are you guaranteed to return another element to the set? We get that for derivatives in elementary functions, and that's so nice because most of the stuff that we use to ever model any scenario, I mean, have you ever worked with functions that don't fall on that list right there? Like everything you've ever done in your mathematical life so far has been one of these guys right now, or worst case scenario, a piecewise function involving some of those parts, right? So the point is, we've been able to take the derivative of every single function that we've pretty much ever worked with in our entire lives, and that derivative returned back to us another function that we recognize, something else that we've worked with, an elementary function. On the other hand, we are not guaranteed to be able to analytically integrate an elementary function and get back an elementary function. In fact, many functions that seem very simple have been proven to have no elementary antiderivative. These 6 integrals that are on the screen right now, there are proofs that exist that there cannot be an expression for the antiderivative in terms of elementary functions. And these aren't that crazy. I mean, e to the x over x, that is not that wild of an expression right there. It's not just that nobody's found one yet, it's that people have come up with proofs proving that it's not possible to come up with an antiderivative for that function right here. Sine of x squared, not that weird. Cosine of e to the x, not that weird. Square root of a cubic, not that weird. 1 over natural log, sine of x over x. All of these things, there exist proofs guaranteeing that there does not exist an antiderivative made up of these elementary functions. Now, it's definitely the case that, like, it's not like we don't have a way to express these antiderivatives, but they're using functions that don't fall under this heading of our elementary functions out there, meaning they're these kind of weirder things that even if you could see what the answer is, it's not like you're going to understand how to interpret the parts. But then again, I also like to think, for example, and I had some discussion with this via email this week, with some students in differential equations actually discussing exactly this fact, and that this is kind of a really weird thing. I think a thing to kind of like help you feel slightly more okay about this is this. Think about the number e and ask yourself if you really feel comfortable describing to a stranger what exactly the number e is. And if somebody said to you, well, how do you get the number for e? Could you come up with it? Could you come up with a set of instructions that would lead you to hold the number e in your calculator without using the e button? And I'm assuming that the answer for most of us is no. I'm assuming that a small number of you remember a limit calculation that we talked about in Calc 1 probably associated with this. Although honestly, I can say I don't even know if everybody does this in Calc 1. I do when I teach it, but I don't know if that's a typical thing. We're going to come up with at the end of this semester, it'll be one of our Chapter 11 topics, is we're going to talk about how to come up with the number e by computing an infinite sum. Well, how good do you feel about saying to somebody, no, I know what that number is. Just add up an infinite number of these numbers and you'll get that number right there. Try and convince a random person that it makes sense to define a number based on an infinite sum. It's kind of a weird idea. As we have learned very much this semester and last semester, infinity is a weird thing to throw around like that. So when E was first sort of discovered and its original representation was given as this infinite sum, how many mathematicians around the world do you think were just totally cool with that? And the answer is not 100% of them, right? And so the point is here is that we occasionally run across quantities that are very, very difficult for us to represent in an elementary way as we're defining elementary functions, but that doesn't necessarily mean they're not useful. And so I like to think that the job of a mathematician is not to do computation. It is to recognize computations that other people can't do and study them enough to understand why we might want to sort of bring those into the fold, so to speak, to kind of say, listen, this is an operation that we should all now get on board with, e to the x. there was a time in human history where the concept of e to the x was literally what we would define as cutting edge technology, the most advanced mathematical knowledge on earth. That's a weird thing to think about when there were people that were not down with there being numbers that we had to use an infinite number of decimals to represent or an infinite number of terms in an addition to represent. That takes some getting over a little bit of getting used to, where people said, listen, this is just how the number is defined, and it's useful enough that you kind of need to get over it because look at all these things that this number helps us understand. E is that useful to us, and so we brought it into the fold, even though its definitions, in any way that you swing it, E requires infinity to define, and that's tough right there, right? So this is just difficult for us to kind of come to grips with right here, right? That there's not just integrals. It's not like you can't do them because you're just a Calc 2 student. It's that mathematicians that are 10 times what we'll all be collectively in our lives have proven that these straight up cannot be done using what we would love to use, which is elementary functions. So that's just a tough place to be. So it's good to like really stop and acknowledge that like when we say integration's hard, what I really don't mean is I don't mean this class is hard. Obviously this class is hard. That's not what I'm talking about when I say integration's hard. What I mean when I say integration's hard is this phrase right here. That when I think about integration being hard, I'm saying that in my mind is a comparative statement to differentiation. And again, I could give you a function that's the product of 17 different functions that are all compositions. I still consider that easy because I know exactly what I'm going to do. Even though it might take me 4 hours to write out my response to it, at no point am I confused except for maybe making some translation errors from one line to the next, right? There's no strategy that's really involved. It's like do the hell out of the product in the chain rule. Like that's it right there, right? That's just we've learned that integration is not just like effort based, right? That there's like deep strategy that's involved with it. And that's just for the surface level ones that we're handling in this class here, right? So kind of, I think it's good for you to like stop and like adjust what you mean when you say to yourself, man, integration's hard. Because I think that a lot of us just think of it as like, my homework was hard. That's not what we mean when we say that integration's hard. We mean it's actually just straight up mostly generally not doable by like anyone, not just you and your my open math homework, right? So I think that's one good like philosophical thing for all of us to sort of take a moment to do in this class is to really define what we mean when we say integration is hard, more than just a difficulty rating. Right? So let's talk about some special ones. One integral that I find of particular interest that I think is an extra interesting one that we can't handle is the integral of e to the negative x squared. The reason why this one is special in all the realm of non-integrable functions is because this is the essential baseline function associated with the normal distribution right here. That's what our e to the negative x squared is going to look like right there. This is defining the normal curve, which is like the number one most used function in all of probability. In probability, what we want to do is find the area underneath probability distribution functions like the one that I just drew to determine the probability of an event occurring. Well, the whole point here that I'm bringing up is it's literally not possible to determine an antiderivative for e to the negative x squared. But e to the negative x squared is literally the function that describes the normal curve, and the area underneath a region of the normal curve is the probability of that event occurring. It's the most wildly used thing in statistics and probability is computing area underneath the normal curve, and 100% of it is done with numerical approximations because there is no way to get an antiderivative for this thing directly. We will see a roundabout technique that we can use out there in chapter 11. It's really complicated. There's not a clean way to express any antiderivative for e to the negative x squared, right? So this is a really important function to be able to integrate, and we straight up can't, right? Now, in section 8.4, out there in chapter 8, our next applications chapter, right? All of chapter 8 is more applications to integration. We're going to get things like arc length of a curve, surface area of a three-dimensional surface. We're going to cover a probability section out there, some good stuff like that. So section 8.4 I really like because I really like discussing probability topics. I think I've yelled at you guys about this before that I really have a great appreciation for probability and statistics. Teaching introductory statistics is incredibly difficult for me because essentially everything in probability and statistics is at its core defined by calculus operations, but nobody has ever really taken calculus when they're taking introduction to statistics. Usually I have like one person, and usually they've just taken Calc 1, so they still don't even know like the integration techniques that we'd need to define most things that are happening in statistics. So I love it as a topic. I greatly struggle to teach it as a class because it is sort of before you learn where all the math is actually coming from. And so I constantly have to be like, oh yeah, you just go and get a number from a calculator. And if students ever ask me like, well, how's that number calculated? I'm like, go take 3 semesters of calculus and then I can tell you. And it's a very demotivating return response for me. So I try to not say that, but that's what pops into my head when I get those questions and stats out there. So very important function. We would love to be able to come up with an expression for this antiderivative. Don't have one. All right. So let's look at some things that are related to this and like see how we feel about some nearby functions. So here's what I want to look at right here. Here are some functions that are near to this e to the negative x squared. And by the way, that negative up there is just not what's causing our issues for our ability to do the antiderivative. That's a constant multiple. That's not our issue in trying to take this integral right here, right? So notice down here, I've dropped the negative from these guys right there because that's just a constant multiple. All these guys have the same types of issues as this one's going to have right here. So what I want to know is, what do we think we can do here? Can we do any of these nearby functions? Which ones seem reasonable to us and which ones don't seem reasonable to us right here? What do we think's integrable and what isn't? Well, let's take a look at these, kind of see which ones might work, see which ones aren't going to work, see which ones are going to kind of fail for us here. And kind of right away, the thing that I'm thinking is, if I know that we don't have an antiderivative for this guy right here, I'm thinking that we probably aren't going to be able to come up with this one. It only differs by a single negative. Constant multiples shouldn't affect our ability to differentiate or integrate. This guy right here seems to have the one piece that I wanted it to actually have right there. You should notice that our issue here is that when there's a single x squared but no other x components, that ruins our ability to do u sub. But here, since I am multiplying by a 1 degree lower polynomial of x, it actually seems like I'm going to be able to u sub this thing with u being x squared and du being 2x dx. I've got x dx in this guy right here. So I think that this guy should work out with some u sub right there. I feel reasonably good about that being possible. What do we think about this guy? Well, now we've got x squared e to the x squared right here. So do we think this one's going to be doable here? This feels to me like u sub's no longer going to work because I don't see a component and its derivative in there. But now I'm maybe thinking that maybe something like maybe integration by parts or something, because I don't know, this x squared e to the x, I know for a fact I can do with integration by parts. I don't know what that e to the x squared right there. I'm going to give this a question mark, and I'm going to put IBP next to it. I'm going to think to myself, that feels to me like maybe an integration. At least that's the only strategy I can think to try, at least. And then this last one over here, I don't know, is this helping us at all to get even more terms that are in here? This one, I have an even harder time saying I think I know the strategy I would try. At least here, this seems to be yelling at me, hey, Tony, try integration by parts. This one isn't yelling the same things at me, so I'm going to give this one a question mark with a frowny face right there. It's not clear to me that that's going to lend itself any better or any worse to any of our strategies that we're coming up with right there. So that's sort of my guesses. My guesses, I think no, I think yes, and then I don't know, but I know what I'd try, and then I just straight up don't know for the fourth one right here. So let's take a look at these, and again, this is the whole point of this is saying like, where do we live within the realm of integration and how should we go about like investigating things that are like this here, right? So the things that I'm thinking here are like, I don't know. What are we going to do with this integral of e to the x squared right here? I think I should probably just bump down right away here. What are we going to try? Well, the thing that I feel like I want to try in this case right here is it feels to me like I should be trying some like u sub or something like that. I feel like I want to do something like u being x squared. And if I did this, then I would get down to du equals 2x dx, but I don't have that, right? So like I don't know. If I want to like really try and force some substitution to happen here, I feel like I could maybe do something like du over 2x is dx, right? I could do a little bit of weird division like that. maybe this would help get me somewhere. So this will get me e to the u times du over 2x. So I'm really looking at 1/2 integral of e to the u over x du. And I want to get this thing in terms of u. So maybe then I would say something like x is the square root of u if we're considering only positive values right here, which is not necessarily the case in our standard normal distribution is split 50-50 positives and negatives right here, but okay, anyway. So I don't know, we're going to get down to a 1/2 integral of e to the u over square root of u du. Um, mm, does it feel like I don't know? So maybe then we could take this guy and say, so this really should be like a u to the negative 1/2 e to the u du. Well, I don't know. This feels to me like I don't feel like I see any u sub action happening here, but maybe there's like an integration by parts that we could do or something like that. Um, if I picked my integration by parts term to be the u to the negative 1/2 and my dv term down here to be e to the u du. V would be e to the u, but my dm term here is now negative 1/2 u to the negative 3/2 du. I don't feel like I'm helping myself. I feel like I'm going in the wrong direction. I've now just increased that power to be to the 3/2. It feels like this is going nowhere, is basically what I'm trying to get at here. I don't know anything else I could really try here other than some u subs and some integration by parts. But integration by parts is never going to help me in this case because these fractional powers are never going to sort of dissipate as we've seen them do with our u's and with our dv's if we're trying to increase or decrease the power. And otherwise, if I didn't do the u sub first, then I'm guaranteed stuck with this composition of functions, which is going to make my, if I try to do integration by parts first, including this in a dv term isn't going to get me there, and including this in a u term is going to introduce more powers of x rather than less out there. So it doesn't seem like we're going anywhere with this guy is the bottom line. We could keep on trying to finagle, swing some terms around. Every integral I'm getting at looks no better than any previous right there. So I don't know. I shouldn't say I'm convinced, but I certainly don't see any route to do it. And again, I know that this has no explicit antiderivative in terms of elementary functions, but these are like the things that I might try. But I'm seeing kind of the like going nowhere work that I've got going on here. So let's stop and feel good about ourselves for a minute here and say, now what happens if we introduce this coefficient of x onto this guy right here? Well, this screams u sub at me because I see an x squared and I see an x, and I know that one is a constant multiple of the derivative of the other. So this seems to me like doing our u equals x squared and our du equals 2x dx and our 1/2 du equals x dx. That's going to work out great for me, right? This is going to give me now 1/2 integral of e to the u du. And that's just going to give me 1/2 e to the u plus c, and that's going to give me my 1/2 e to the x squared plus c. So it does look like we're able to come up with this guy right here, and this one honestly is pretty dang easy. This is like one of our first ever u sub problems right here. I know that all of you guys did essentially this exact one in like a My Open Math homework right there. That one, I am hoping that when you see that problem, that u sub is just smacking you in the face right there. A function and its derivative are both just staring at you in this expression right here. And u sub we use to undo that the chain rule. We absolutely have that composition of functions that is our indicator of doing a u sub right there. So this has all the trappings to me of a classic u sub problem, and it does work out nicely for us. So what's up with this guy here? Can we do this one with our x squared term in here? Let's take a look. Let's see if we can finagle a way to make this guy happen. So here's the thing that I'm thinking to myself. I'm thinking to myself this. My first thought to myself here is I don't see a u sub, and the reason u sub doesn't look great to me is because I feel like I'd be obligated to pick u being x squared. But then and in fact, I'm just going to write some of these things out. I'm going to write number one. If we did a u sub with u being x squared, then we'd have to have du being 2x dx. But it seems to me then like I'm going to be introducing like partial terms out here that I don't know that I can actually handle with this thing, because if u is x squared, then we should be getting an integral of u e to the u. But then I don't really have a way to rewrite my dx right here. We're going to end up with like maybe a fractional power of u if I did this like very awkward little swap around like I did right here, the du over 2x. Like I could do that again. But we're going to end up in the same boat where we're going to get like a u to the 3 halves power. And then we don't have any way to actually deal with that thing since we can't u sub it away. And integration by parts would take us from 3 halves to 1 half to negative 1 half. It would jump over just not having the thing right there, or by having one whole account of it. We'd be stuck with the fractional powers and we'd never be able to undo that right there. So it doesn't seem like that's going to be a helpful route to go for this guy with this one. Another thing I could think to myself, another strategy I could choose here for strategy number 2 is I could say, let's integration by parts this guy. If I were going to do that, then what would be my natural choice here for u and dv? Well, the way that I would want to pick this, based on what my instincts tell me about integration by parts, would be to do like an x squared right there. It's a pretty classic move with integration by parts with a product, is you want to pick your polynomial factor to be the u term so that the du term is 1 power lower. We would reduce our situation here. So then we'd have a 2x dx. That's now got me down to just an x to the first instead of an x to the second. And that would be excellent because I know that I can integrate with that x to the first with an e to the x squared in here. But what's the problem with this one? Well, the whole problem with this one is we can't get v, right? The whole point is I would need to be able to integrate e to the x squared to get v, and the whole thing that we've already talked about is that we can't integrate e to the x squared. So it doesn't seem like that's going to work out for us either here. What else might we try here? Well, one of the things that I'm kind of recognizing is that there's value in having a single x that's separate from the e to the x squared right there. A single x, not two x's, right? So maybe a third thing that I could think, a third strategy that I might try here would be to rewrite this where I just pick off one of these separately, right? So maybe I'm thinking of this as x times e to the x squared dx. In this case now, maybe I could pick for myself some integration by parts setups that might do this guy for me here. If I did this, then now maybe I can pick u to just be x. So let's let u be x, and therefore du is dx. That one's nice. Then I can pick dv to be x e to the x squared dx. And this I have an antiderivative for, right? I can get v. I've got it sitting right there. Here's my integral of x e to the x squared. That's what I need for this guy. I'm going to get 1 half e to the x squared. So it looks like I can at least set up this integration by parts. I don't know if it's going to get me to an integral I can actually do for the second round of it, but like I can at least get past step 1, which is a first so far for this problem. So if I did this then now it looks like I've got this. It looks like I now have the integral of what I'm seeing here. Oh, excuse me. This is my, I want uv. That's what I'm doing wrong right here. I want my uv minus integral v to u. So uv 1 half x e to the x squared. That's my uv. Minus integral v to u. Can we do the integral of v to u? V du is going to give us minus 1 half e to the x squared dx. How disappointing. We are now back at the place where we don't have an antiderivative for this and we got stuck. It at least seems like this was sort of like the closest. We at least did improve the situation of this integral right here. We at least reduced it down to something simpler. So I at least feel like I can say this was our closest, but who cares because we still didn't get there, right? So I still don't have a way to proceed on with this guy right here. I still can't do that integral. And we tried some things, right? We tried some u sub. We tried several different integration by parts selections right here. It doesn't seem like any of these things are going to work me towards an integral that I can technically handle. So it seems like this x squared e to the x squared, as far as I can see, it doesn't seem like there's going to be any antiderivative that we can get out here. But it did seem like we were able to at least convert this into our original difficult problem of just e to the x squared right there. So as our last one of consideration here, let's see this guy right. Oh, Don't. Oh, come on now, Microsoft Word. There we go. We'll be friends today, I promise. There we go. So this last guy right here. Is there anything that we think that we're going to be able to do? Wait, didn't I just give myself all? Okay, never mind. I don't need that extra room right there. Let's bump this guy back down. Okay. So let's go ahead and look at this last one right here. So what are we going to do with this thing? Well, this doesn't look promising to me because this just looks like even more components that are going to be integrals of e to the x squared. Now, at least what my integration intuition is telling me is this. The only way that I would really want this leading factor right there to remain in that factored form is if it was going to be like the derivative of some other function, right? If this power up here was like x plus 2/3 x cubed or something, then that would be exactly its derivative, and I would want that written in that form. Since it's not, doesn't seem to be some good reason why it's all one collective term right there, it seems to me like doing the distribution and ripping this up into two integrals seems to be the smartest choice that I could make here. So let's go ahead and do that here. If I were to rip this up, this would then become the integral of our nemesis, e to the x squared dx, plus 2 copies of the integral of x squared e to the x squared. Well, that kind of sucks right here because these are just the two things that we've already proven that we can't do. But notice one really nice thing that's actually happening here. What happened when we tried our hardest to do this integral? What was the best thing that we came up with? So we came up with a response that involved something that we were able to compute and a negative of an e to the x squared integral. This is a positive of an e to the x squared integral. Maybe let's see if we can make this guy happen. So what do we got here? 2 times, I'm going to get my uv, u times v. Oh, wait a minute. Didn't I write this wrong? Sorry, I wrote this wrong. That's not 1/2 x e to the x squared. That's just 1/2 e to the x squared. I'm just copying down my result from up above up there. There we go. And now that means I need to fix that right there. So u times v is just 1/2 x e to the x squared. 1/2 x e to the x squared minus integral of v du. V du is going to be 1/2 e to the x squared dx. Check out this nice stuff. Oh, baby. Well, holy cow. It looks like we actually were able to pull that guy off. We were able to pull it off because it contained 2 components of integrals we couldn't do that canceled away from each other. And these are ones where like I don't know if this should feel satisfying or if this should just piss you off right here because like the whole point is like we built 2 impossible components that canceled out. And that's just sort of laughable to me, the way that some of those things work out right there. But what I want to tell you is that these types of strategies are kind of really, really common in math where we get really stuck with not being able to directly evaluate something, but coming up with multiple alternate expressions for it and realizing that we can combine their ideas to get the final answer is pretty interesting. You guys actually kind of did some stuff that's sort of related to this idea with our dump truck integration. When you do integration by parts twice with your sines and cosines, realize that they cycle back around, you end up with your integral being equal to some other integrals, but those integrals were like terms, so you just added them together, divided by the coefficient. Excuse me. and we're able to claim its final value right there. Pretty cool. Pretty cool that actually works out nicely. Some other places that I've seen this happen, and by the way, this is kind of related to some stuff that we're going to see later this semester. This last summer, I kind of like did some work through a textbook that dealt a lot with summations and how do we evaluate sums that are really difficult. And one of the very cool techniques that I learned from that textbook is that when we're trying to evaluate a sum from I equals 0 to n of some f of I sub x right here, that the move is to come up with two different expressions for the sum from I equals 0 up to n plus 1, so to include an additional term, two different versions of it. Then what we can do is we can pick off the n plus 1th term, but we can set those two alternate expressions equal to each other, and we can cancel away the original sum that we didn't know how to compute and just see the remaining value of the sum being built by the n plus 1th terms of the adjusted sums that are out there. So this is like a method of perturbation. You adjust the thing that you're looking for slightly, realize that the thing you're actually looking for is one component of the adjusted thing, and then come up with more alternate ways to show the adjusted thing, group some stuff together that you couldn't handle to let it all cancel away, and just be left with the extra parts that you introduced right there. A very sneaky roundabout way to come at evaluating some of these things right here, but a super cool thing. So this like broad strategy right here of introduce more parts so that they can cancel off with the parts you couldn't handle. It's a thing that happens in like 1,000 different ways in 1,000 different branches of math out there. So again, I don't know if you should be very happy with your ability to do this or like annoyed, but it's kind of cool either way here. Um, so yeah. Yeah, Adrian, these are things too where you're saying, it's not clear that you spent like a ton of time on this section last spring. Yeah, it's like, sorry, are you talking about with the summations there? And this is just one of those things where like dealing with things like sums and honestly dealing with things like difficult integrals is a thing where it's like, is it worth our time to all take like 3 semesters on like integration techniques and summation evaluation techniques? And it's like, just because there's an infinite number of things that could possibly happen out there, there's sort of like diminishing returns eventually, right? It's like how much time do we really want to spend on, or should we take entire classes on evaluating sums? But then again, like I'm saying to you, I've gone to grad school and I dealt a ton with sums in grad school, especially in all my probability and statistics classes. And I can tell you guys, I learned a ton last summer by going through the first 3 chapters of this book on discrete mathematics. By the way, if you're looking for a good one, this is called Concrete Mathematics by Donald Knuth. Super good book. If you're looking for some like a little bit of math stuff to do and you're not going to allow me to be convincing you that you should be doing programming, then I think that's a book that you should go and just peruse for some little like side content for yourself. Basically, Donald Knuth is, I think he's like an emeritus CS professor, computer science professor at Stanford. He's still alive. He is the guy that invented LaTeX, the like typesetting language where you get to type fancy math programming stuff like that. He's officially a computer programmer, computer science professor. But what he realized is that all of his computer science students weren't good enough at math to do the computer science things that he wanted them to be able to do. And he wasn't able to get the math department on board with the math that he wanted them to teach for his computer science students. So he wrote a math textbook as a computer science professor that's sort of like what kind of like hardcore math do you need to be able to do to be super good at being a computer scientist. And this is now kind of generally regarded as one of the best. Like a lot of people, if you go ask a bunch of math nerds, like, what's your favorite math textbook you've ever used? I see this end up like in the top 3 all the time, all the time. It's written by not a math professor out there. Yeah, and LaTeX is awesome. And so this is the guy that came up with it. He wrote this great, and again, I've just heard about this book like 100 times. And so finally this last summer, I was like, cool, I'm gonna go poke around in that book here and see what I can see. And I learned a ton. Like all these techniques were like I was doing problems and I was like, I can't believe that worked out that way. Like over and over again. It was really cool stuff. Really well made book, and it's a bunch of stuff that like it's not like it's super high level stuff. It's just stuff you haven't seen. It's stuff that's easily accessible to you with how much math you know. But it's like techniques that you've just never even considered before to like kind of handle problems like that. So Donald Knuth, top three favorite living mathematicians, and he's not even a mathematician; he's a computer scientist. But cool guy. He's also you should look up some other things if you're going to do nothing else. Look up Knuth up arrow notation. This is your Wikipedia homework right here. And so Donald Knuth, also for computer programming purposes, invented what is essentially hyper exponentiation. We go addition to multiplication. We go multiplication to exponentiation, but shouldn't we be able to go exponentiation to something like next level? He needed to be able to express some like numbers that are like a couple hundred digits long in a more convenient fashion. And so he came up with a new idea for how to do that. So that's also kind of he invented this idea of hyper exponentiation, which he indicates with some up arrows, which is why it's called Knuth's up arrow notation. So really interesting guy, really interesting guy. In some way, shape, or form, you will have interacted with ideas of Donald Knuth likely in the next couple of years of your life if you haven't already here. So interesting stuff, interesting guy right there. Okay, enough about our integral problem right here. I get all excited and sidetracked about these topics here. Okay, so let's talk about our strategies now for integration, right? The name of this section is strategy for integration, and we haven't really talked about that. We've just had like a heart to heart about how this has been really hard for us, right? Well, what you really should do is go read your section 7.5 in the book. They're gonna give you like a broad set of strategies for like what should you do when you're approaching just any old integral that you're seeing and you don't know what to do. All right, and here's kind of their general advice. I sort of simplified the things that they said here a little bit, so I do very much think there's value in reading the books. The book has like one really nice full page, and it's like a step-by-step checklist of being like what things you should try and in what order you should try them. I've condensed a little bit. The thing that we should realize that we've always been doing, and as I've shouted at you guys 100 times by now this semester, is algebra is the hardest part of this class, sort of in a sense because it's the most important part. If you don't do the algebra first and last well, then you're never going to be able to make the calculus in the middle actually happen. So our step one with calculus always is saying, since calculus is hard, you should make sure that you're doing the easiest calculus you can, and that's by algebraically manipulating the expressions that you're going to be dealing with first to be in their simplest possible forms. One good little hint I'll give you guys here is don't forget about conjugates. Remember that multiplying by the conjugate is always a good way to alter the terms that you're looking at, right? This is our like x plus y times x minus y. That's the conjugate right there. That's our conjugate of x plus y is x minus y. Same terms, different sign between them right there. It's a good way for us to like just kind of, mix it up a little bit. Get some terms that might look better for us. We definitely see it that helps out in trig situations because conjugates create squared terms where there weren't squared terms before. Squared terms play really nice with the Pythagorean identity, so that's definitely a good strategy. And I've got that sitting right there also, trigonometric substitutions. Other ways that we alter what our integrand looks like is by saying it's hard for us to deal with lots of terms under square roots. It's hard for us to deal with squared terms when there then aren't associated linear terms also in the integrand. And so sometimes trig substitutions, again, help us kind of shuffle some things around. Pythagorean identity really helps us play with squared things nicely. The second thing you should do is you should hope for the easiest type of integration special technique that we have, right? We hope for U substitution because U substitution is always pretty easy, right? Identifying one component in the integrand whose derivative is also in the integrand, but remember, there are sort of U sub extensions where it's not necessarily just finding derivatives that are in there. Remember that we did things like doing, what was it, like x times like x minus 5 to the 1/2 or something like that. Well, then we would rewrite this as like a u plus 5 times u to the 1/2 by doing the substitution of u equals x minus 5 and then x equals u plus 5. So here where I'm saying one component wasn't a derivative of the other component, but it was a linear transformation of the other component. So we don't get new terms when we go from dx to du, but we are able to write things in an alternate format that allows us to then just multiply out that u expression and directly take the antiderivative right there. So don't forget for u sub, it doesn't only handle our chain rule case. The chain rule case is when we see one component and its derivative. That's undoing the chain rule. We also get to handle lots of cases where a linear transformation being applied to the thing, a shift left or right, or a multiple by 2. Well, even the multiply by 2 is really more of like a u sub, or more of a a chain rule thing right there. But in any event, linear transformations also handled nicely by usub. So don't forget that usub kind of has that second little job for us. If neither of those things are going to work out, then we should try to classify the integrand according to its form. If we see powers of trig functions, then we know that there's a set of suggestions for us in 7.2 that tell us what substitutions we should make for the trig functions. If we see rational functions, we know that we might want to think about partial fraction decomposition. We also might want to think about more trig substitutions. Integration by parts. If we have a product of a polynomial and a trig or an exponential and a log function, great integration by parts scenario. You guys have also seen that if we have products of just these types of things, you guys did in your written homework that was due last week for our trig exponential stuff right there, e to the ax times sine of bx or whatever that was, that also lended itself well to integration by parts. Remember that integration by parts is derived from the product rule, but it does handle things for us other than just the product rule. So remember that products are closely associated with this, but also remember for integration by parts, that's where we got like our integral of natural log of x dx. That was an integration by parts problem, and there's no product rule that's really happening there unless you think of natural log of x and dx as the product, which we typically don't, right? So like integration by parts is a little bit weird because it handles a pretty broad perspective of things. It handles a lot of things well, like an inverse product rule would, or a backwards version of the product rule, but it definitely does things that are also other than that. Oh, and Asia, great call, posting the link in chat right there. I'm going to scroll back up here and say what you're saying right there. A really awesome thing is that Concrete Mathematics. If you go look it up on the internet, you'll find the third edition for like $150. You'll find the second edition as a free PDF out there, which is exactly what I downloaded when I worked through it. So I was not in the newest edition. I was looking at the second edition, which is a free PDF out there, meaning there's no roadblock to going and perusing some of the very cool topics that are early on in that book right there. So second edition of this is freely available online. So no excuses. Good call with that link right there. And our other things out here, whenever you see radicals, our two strategies that we've seen for radicals are trig sub if there's squared terms underneath the radical, but when there's not squared terms underneath the radical, sometimes it works out for us to u sub out the whole dang radical expression. That was what we ended with in our last video yesterday when we were doing, at the end of our partial fraction decomposition, I was doing that like 1 over x minus the square root of x plus 2 or something like that. I think was the one that we ended with. It was like a 1 over x minus square root of x plus 2. And this one worked out best for us by doing u equals square root of x plus 2, which doesn't really feel like what I'm used to doing. When I'm thinking u sub stuff, it's usually I'm trying to undo the composition of functions, meaning I would grab u to be x plus 2, but that didn't help us in this case right here. Instead, it seems like sometimes when square roots are involved, it's actually sometimes helpful to grab the whole dang square root rather than just the expression that's contained within. And again, if it doesn't even occur to you to try that, then you'd get stuck on problems like these. And so what we're really looking at today when we talk about strategies for integration is like realize what your checklist is so that you don't miss a possible route to a solution. And that's where I'm then going to say the most important advice I could ever give you ever for all of calculus ever is you need to try more than one thing. If you're going to give up after you didn't get it on the first try, then you're just probably not going to be a good mathematician in life. Persistence is key. You have to keep just trying stuff out there. Don't give up because there's so many things that we might want to try. So like, try them. And if you try just the things at the top, then you're only going to be able to handle kind of the most boring integrals out there. So don't just do that, right? Know what your checklist is, know a strategic way that you're going to proceed through your attempts at any given integral, and keep trying stuff out there. Every single non-basic integral we've done has boiled down to a substitution, an integration by parts, or an algebraic manipulation. And so I'm saying here, integration, I don't really think of it as an academic battle. It's an academic battle if it matters if you can come up with the solution for an integral in 2 minutes, which I never will care if you can do. Therefore, It's more of a psychological battle with yourself of you saying, you know what, damn it, I'm not going to let this integral just scare me like this. I'm going to actually just make this happen. I know you guys have heard me verbalize this many, many times. I don't think of algebra and calculus as like these, I don't know, we refer to these as like our tools in our toolkit that we're building. I think of them as meaner things, and maybe this is just like the dude in me thinking about this stuff. I refer to these things as my algebra beating stick and my calculus beating stick. I don't think about this nicely, right? Because if I think about it nicely, then that integral might be able to take advantage of me, and I don't ever want that to happen. I think about this aggressively because I know that I am competent enough to be able to handle these things. I picture these as being a fight that I know that I'm going to win, that I know that I'm going to win. When I say I know that I'm going to win it, that's the psychological battle that I'm referring to right there. I never convince myself that I'm just going to get bested by some integral unless I know that it's not integrable. Then I'm like, no, I'm good enough at calculus. I'm going to make this thing happen. And I picture myself getting in a freaking fist fight with this integral. Never been in a fist fight in my life, but in my head I've been in millions, and it's all been with integration and programming. Programming is also a thing, although I do get afraid of writing programs, whereas I don't with calculus that's out there. Yes, step 5, release your anger. Let your anger be your guide here. Yes, good. And I agree with you, Asia. It's not just a dude thing. This is I don't get taken advantage of by things that are just math problems. I'm the thing that does the deciding if it's going to happen or not. Don't let yourself be convinced that you can't do it. If you don't have persistence, you need to develop that degree of mathematical endurance where you don't give up. You strategically try things. You don't repeat your same work over and over again. Smart strategy means that you're going to be able to chop down that tree with a baseball bat faster than it seems like you think you otherwise might be able to. I don't know. I think that there's value, and I know that I don't think this is like a common phrase that you're going to hear in lots of calculus classes. I think there's a little bit of value associated with aggression related to calculus stuff right here. Because it's not easy. If it was easy, then we could all just be nice about it. It's not. And so we have to be a little bit aggressive about it. And I think that that's valuable. And the other advice that I'm giving you right here is don't just be aggressive like an idiot where I'm talking about chopping down a tree with a baseball bat. You need to remember to do yourself some favors every once in a while. Don't go reinventing the wheel every time that you're trying to do a new problem. The reason that I wrote this one specifically is because some of the hardest integrals we've done so far this semester are the ones that crop up from our moves right here. If I'm looking at this one, what I want to remember is that when we talked about our trig substitutions back here, wherever I'm looking for my trig substitutions, our trig substitutions up here, what we should look for in step 1 is it is suggested to us that if we have even powers of tangent with secant, that we should just do our swap for tangent to rewrite this guy as 1 minus c, or excuse me, I always get this one backwards, by the way. I usually have to go kind of remind myself about what this guy is right here, but secant squared of x minus 1 times secant of x. When we get to here, look at what we've got. We've got our integral of secant cubed of x minus secant. Both of those were sort of a bear to do. The integral for secant is straight up a trick that you would never think of. The integral for secant cubed is going to introduce the integral of secant, so you'd need to be able to do the trick either way. We reuse our old results. We did that once for a reason so that we don't have to do it again. Reuse your old results. Those were hard integrals that you should never be able to. And even though I know it's a trick, right now I'm literally trying to think to myself, what was that trick that we did for secant? I think we multiplied it. Wasn't it like secant plus tangent over secant plus tangent, I think? But the point is, a month from now, I straight up won't even remember. I'm only remembering because I did this like 2 weeks ago, right? Like, all I remember is that there's some like weird trick that I don't remember to it, right? Stuff like that that's dumb. Reuse our old results. We already did this one for a reason. Don't go have to reinvent the wheel every single time. Be aggressive, but also be smart. You know, that's kind of the final advice that we're given right here. And that really matters. I can't say that this is good advice in all my other math classes. In integral calculus, this is good advice right here. Develop endurance. This is always going to be hard. So What I want to do now that we've talked our philosophical and our emotional component to this course right here, which I think is very relevant, not to all math classes, but definitely to this one, let's go and look at some good problems right here. There's two problems that I want to do today just to kind of show like all these strategies that we've seen out here. I'm going to do some U subs. I'm going to do some parts. I'm going to do some trig subs. I'm going to do some partial fraction decomposition. I'm going to use some trig identities. I'm going to do some conjugates. All of those things are going to happen and only two integrals coming up right here. So we're going to do two different integrals right now and call it a day for our strategies. But these are integrals that can be done in wildly different ways that all require some good thought, some good strategy. So first we're going to look at a trigonometric integral right here. We're going to do this one two completely different ways. Then we're going to look at, and give myself a lot of room right here. Then we're going to look at this gross looking radical integrand right here. We're going to do this one two different ways. Oh, the second way we're going to do this one is going to be the hardest integral we'll have done this semester right here. We're going to do it one way that's going to work out kind of nice, one way that's going to work out less nice. But I don't care because I don't care about nice with integrals anymore. Nice isn't a word that I use with integrals. I can either do it or I can't. And those are the two ways that I classify integrals. I can do this one. And that's the thing that matters to me. So let's go ahead and hit these two guys here. And this will be kind of our cleanup for our day right here. So this first guy right here, we got some nice trig quantities in here. And there's really two broad strategies that I could think of for myself with this one. One thing that I like to think about when I see this tangent cubed and this cosine cubed is this. One thing I think is this. One thing I like to think is, I like cosine more than I like tangent, but tangent's made up of sines and cosines. So one of our possible strategies here might be rewrite in terms of sine and cosine, see if we can make it happen from there. All right. Another strategy that I'm thinking about that's associated with this. Yeah, Asia, good call. Yeah, I agree with you. You can tell the Math50B students on campus because of the confused and frustrated face followed by 20 minutes afterwards of glee. I totally agree with you that I think that differential equations and calculus 2, which I'm teaching both of this semester, are really where I took my great appreciation for math over the edge. It used to just be in third grade, I could do multiplication in my head faster than other people, and that's where I got the satisfaction from it. But it wasn't that I ever got jammed up until this class, basically. And this was the first time where it was ever a hill I had to climb. And then it felt good to get to the top. And that wasn't a comparing myself to other people thing anymore. It was a comparing myself to myself thing. And I think that's why it brought me that deeper inner pleasure that you're referencing being visible on my face right there. It wasn't, I don't know. Everybody's better than somebody else at something. Mine happened to be mental math, and that was a thing for years when you're young. But it didn't get to the point till now where it was I thought I couldn't do a problem and then I did. And I was angry and then I was thrilled. And so, yes, to me, there's an emotion-based component to this right here. So let's hit this tangent cubed and this cosine cubed right here. The other thing that I'm noticing, if I weren't going to go this sine or cosine route, is I'm seeing that I have some powers of tangent. And I know that there was some suggestions that were given to me about what I should do with powers of tangent. But I'm also remembering in our book that the powers of tangent were tied to some relation to secant. But I'm seeing that I have secant in this integrand here. It's hidden. It's 1 over cosine cubed. That's really secant cubed right there. So it seems like there's two different routes that we could take with this guy. Let's go ahead and do them both. So my route number 1 on this guy is going to say, let's rewrite this guy as really being tangent cubed times 1 over cosine cubed. And then say that's really sine cubed over cosine cubed times 1 over cosine cubed. And so really I'm looking at this integral right here of sine cubed over cosine to the 6th. All right. So this is one of my possible strategies, the convert everything to sine and cosine strategy. And I just want to kind of remind all of you, in trig class, this is a good strategy 95% of the time. In calculus, this is a good strategy